I am Dr. V. Leela Vinodhan. Today I am here to discuss a few things regarding the Rankin cycle. So, I am coming from mechanical department from Amet University. Today electricity made everything possible. It makes life easy. So, without electricity, just imagine a world with no lights, fans, TV, refrigerator, washing machine, and day to day life become very difficult if you consider a world which is having no electricity. So, the electricity generation is very important. Today I am here to discuss a very important topic on how electricity is generated, especially how electricity is generated from a steam power plant, because when we consider in the worldwide, the steam power plant generates more energy. So, this particular topic, Rankin cycle, which explains about the basic principle of working of a steam power plant. It basically tells about the components and how and what are all the process that happens in the Rankin cycle, and which is the principle of the steam power plant. This shows the general layout of a steam power plant. Basically, it consists of a boiler, turbine, and the turbine is connected to an electric generator, and from that the turbine, the steam will flows into the condenser, and again it fed back to the pump, and again it goes to the boiler. So, the stack will be there. So, the combustion gases will be fed to the stacks and it be led to the atmosphere in the open air, and the condenser will be connected to a cooling system. Basically, in most of the cases, because of the water conservation, in many places we use a cooling tower. Basically, this cooling tower, it will be associated and it will be placed very near to some sort of water resources. The Rankin cycle. So, basically this is the this is what the basic principle of a steam power plant. So, if we see it have a basic component of a pump, boiler, turbine and condenser. These four components are the major working components in the Rankin cycle. For example, this pump is being used in our day to day life. So, we know about the working of a pump. So, boiler is nothing but something which will heats up. So, something will be used as a heat source, and then the water is heated to a certain level and the water temperature is increased to a certain level in the boiler. The turbine is something which we call as the steam from the boiler is being fed into the turbine and it is expanded in the turbine. So, this turbine is connected to a generator. So, the steam expanding in the turbine moves the blades in the turbine. Due to the result of that, the shaft rotates. The shaft is connected to a generator. So, through that we will be generating electricity. So, after the turbine, what happens to the steam is the steam expands in the turbine and comes out of the turbine and it is fed to the condenser. The condenser is basically the steam is converted from vapor to liquid phase. So, in the condenser the heat is rejected. The saturated liquid from the condenser is fed to the pump, and in pump it is compressed isentropically and the water pressure is increased and it is fed to the boiler. The TS diagram basically have a saturated dome. So, this saturated dome gives the clear idea about from where the liquid is in the saturated state. To the left it shows the saturated liquid region, and the right side of the dome shows the saturated vapor region. So, let us consider the states 1, 2, 3 and 4, which is marked in the diagram, in the 4 component diagram, basically pump, boiler, turbine and condenser. The state 1 is marked at the before the pump, and state 2 is after the pump, and state 3 is after the boiler, and then state 4 is after the turbine. So, the 1, 2 and 3, 4 states are clearly marked in the TS diagram. So, in the saturated dome, if we consider from state from 1 to 2, it is basically a isentropic compression process which is happening at a water pump. The isentropic in the sense the entropy remains constant, there is no change in the entropy. So, in the water pump the water is compressed isentropically and the pressure is increased. There is a small increase in temperature from state 1 to state 2. This is exaggerated greatly in order to clearly state the state of 1 to 2, because in practical there will not be any increase in the temperature of the water. So, the slight increase in the temperature is due to the reduction in the specific volume. Okay. From state 2 to 3, it is nothing but the temperature addition in the boiler. In boiler, the high pressure and high temperature is maintained. So, the heat source is maybe of anything. For example, the boiler can get heat source from a fossil fuel by burning the fossil fuel, or from a nuclear reactor, or from an exhaust of a diesel engine or a petrol engine. Like some sort of heat source should be there in order to increase the temperature of the water in the boiler. So, the boiler can get the heat source from any kind, it does not matter in this particular place, but here the only consideration is that from state 2 to 3 basically have heat addition. So, this happens at a constant pressure process. The heat addition in the boiler is basically happening at a constant pressure. Okay. So, the Q in, it is nothing but the heat addition in the boiler, which is where the temperature of the water is increased from lower temperature to higher temperature, and the pressure is maintained constant because the pressure is already built up in the pump. So, the heat addition is happening at a constant pressure process. So, the increase of a temperature from 2 to 3, it happens at a different stages, like at the entrance of the boiler, the water will be at the saturated liquid state. So, after getting into the boiler, the saturated liquid state changes its states to converting from water to vapor. So, that happens, and this is clearly stated in the line 2 to 3. In 2 to 3 there will be a upward trend in the TS diagram, and from after a point where it touches the saturated liquid line, it changes the phase from water to vapor. After touching the saturated vapor line, it again the temperature of the vapor increases to a superheated vapor. So, after the temperature increases to a superheated and the vapor quality is maintained above 90. With respect to the Rankine cycle, it have 4 basic components. One is pump, boiler, turbine and condenser. In pump, the process is isentropic compression. Okay. The pressure of the water is increased from lower pressure to higher pressure. The higher pressure water from the pump is fed to the boiler. The boiler is basically where the heat is added to the water. So, the high pressure water is the temperature of the high pressure water is increased from lower temperature to high temperature in the boiler. The heat addition happens in the boiler and the process happens at a constant pressure. So, next in the turbine, in the turbine the process is isentropic expansion process. In the turbine, the high pressure and high temperature water is high temperature and high pressure vapor expands through the turbine and it moves the blade of the turbine. As a result, the shaft of the turbine rotates. The turbine shaft is connected to a generator. So, with this we can generate electricity. After coming out of the turbine, the low pressure and the low temperature vapor is fed to the condenser. In condenser, the heat rejection process happens. The heat rejection takes place at a constant pressure process. So, in condenser there will be a cooling system which is attached to it in order to transfer the heat from the vapor to the liquid. So, in condenser, after condenser, the saturated liquid is again fed to the pump in order to increase the pressure of the saturated liquid. After that it is fed to the boiler, and this happens in a cycle. This is clearly shown in the TS diagram. Here in TS diagram we have a saturated dome. Basically it gives it is the average values of saturated states at different pressure. Okay. So, in the left of the dome, from the top and to the left of the dome, it states the saturated liquid region, and from top to the middle of the saturated dome, top to the right hand side, it shows the saturated vapor curve. So, basically this curve gives a clear idea about where the saturated liquid and the saturated vapor stands. So, the process from 1 to 2 is basically a isentropic compression process. So, that means the entropy of the process does not change, the entropy change is 0. So, that is why it is called as isentropic process. The 1 and 2, there will be a slight increase in temperature. This is greatly exaggerated because there will be very slight decrease in the specific volume, but in practical this much of rise in temperature is not. The temperature increase in the pump is not generally observed in practical. So, here it is exaggerated and shown because there will be a slight decrease in the specific volume. Okay. So, that is 1. So, 1 to 2 is there. Okay. 2 to 3 is basically a constant pressure heat addition. In this, what happens is the saturated liquid from the water pump at a higher pressure is fed into the boiler, and in boiler a heat addition happens. So, saturated liquid turns from, it reaches the saturated liquid, and then after that, after gaining so much of heat, what happens is the saturated liquid changes its phase to saturated vapor. After touching the saturated vapor curve, the vapor is it turns to a superheated vapor. It attains the state 3. After 3, it is fed to the turbine. So, in turbine the saturated vapor and superheated vapor. Okay. So, basically it is a superheated vapor which can be expanded in the turbine. It rotates the blades of the turbine. As a result, this rotation of the blades moves rotates the shaft of the turbine. After it is expanded, and the process is isentropic expansion in turbine. After expansion, it comes out of the turbine, and the vapor is fed to the condenser in order to change the phase from vapor to saturated liquid. In condenser, the heat is rejected. So, from 3 to 4 is basically the isentropic process, which is clearly shown in the TS diagram, and 4 to 1 is nothing but the condensation process, and the heat is given to the pump, and the work obtained from the turbine is clearly shown in the TS diagram. The heat addition and heat rejection is also shown in the TS diagram. The energy analysis of ideal Rankine cycle. So, basically the Rankine cycle have 4 components. 4 components are considered to be a steady flow devices. So, we can calculate the energy analysis easily by applying the steady flow energy equation for each component. So, generally the kinetic energy and the potential energy change of a vapor is considered very minimal when compared to the heat transfer and work transfer. So, it is eliminated from the SFE equation. So, after that it is the steady flow energy equation reduces to Q in minus Q out plus W in minus W out, which is equal to H at exit minus H at inlet. H is nothing but enthalpy. Let us consider the pump, and in pump the work is given to the system. So, there is no heat transfer. So, heat supplied, that means that Q is eliminated from the equation. So, it reduces to the work of a pump. So, basically which we are giving to the system, that work input to the pump is basically given by the H2 minus H1. And if you reduce the equation from enthalpy, basically H is equal to U plus PV. There is no change in internal energy in this particular case. So, we are eliminating the internal energy term. So, it reduces to the volume and change in pressure. The volume is constant. So, we are taking out V instead of V2 and V1. So, the only term which is changing here is pressure. So, the equation reduces to W pump in is equal to volume into pressure. Okay. The H1 and volume can be calculated at HF at pressure 1. It is basically, it is taken out from the steam table, where the HF is nothing but the enthalpy at a fluid state at a pressure 1, and the volume, the specific volume is also calculated in the same manner from the steam table. The specific volume of V1 which is considered and which is taken from the steam table at a pressure 1 of specific volume at fluid state. Okay. Next, let us move on to the boiler. So, in boiler, heat addition is happening and no work is done on the particular system. So, in boiler, so the heat transfer is considered and then the work transfer is eliminated. So, the equation reduces to Q in is equal to H3 minus H2. So, next we move on to the turbine. In turbine, there is no heat transfer, only work transfer is happening. The turbine produces work. So, the equation reduces to W is equal to H3 minus H4. In condenser, no work is happening, only heat transfer is happening. So, the Q out is equal to H4 minus H1. So, these are the standard, these are the steady flow energy equation per unit mass of steam for different components, while considering the corresponding heat transfer and the work transfer for the particular devices. So, the overall performance of the ideal cycle can be given out by the thermal efficiency. The thermal efficiency is basically the net work output divided by the heat supplied. The net work output can be given by the work output given by the turbine minus work given to the pump. So, the equation deduces in such a way that the W thermal efficiency is equal to W net by Q in, which is equal to 1 minus Q out minus Q in. So, W net which is given by Q in minus Q out, which is nothing but work done by the turbine minus work given to the pump. The difference between the ideal and actual vapor power cycle. So, basically in the previous slides what we have saw is for ideal condition, because in practical the isentropic process, that means in pump and then in turbine, it is not generally applicable. So, there will be a slight deviation in the process. So, in actual vapor power cycle, what is making the change, that is we are going to see now. So, two things are very important. One is fluid friction. Why? Because the movement of the saturated liquid in the pipes, it because of the friction, we have some change in the actual vapor cycle. So, what are all the causes? So, pressure drop happens in boiler, condenser and piping system. So, this forces us to have high pressure. So, this requires larger pulp and larger work input. Okay. So, next one is the heat loss to the surrounding. So, this is because of the vapor which is transferring through different pipelines at a higher temperature, which will be losing its heats to the surrounding. So, this put us in a situation that we require to transfer more heat. That means we have to maintain the temperature in the boiler at a higher rate. That means we have to maintain at a higher temperature in the boiler. So, the irreversibility which happens in the pump and the turbine is clearly shown in the TS diagram, and that too in the dotted lines. So, the dotted lines, the discontinuous line shows the actual cycle, and the continuous line in the green shows the ideal cycle. So, the pressure drop in the condenser, irreversibility in the pump and irreversibility in the turbine. This is causing a deviation from ideal vapor power cycle from the actual vapor power cycle. The isentropic efficiency, basically when we consider a pump and turbine operate at a isentropic condition, isentropic process, then the isentropic efficiency for pump and a turbine is calculated. Why we require this? Because we have certain irreversibility happens in the pump and the turbine, because of that there is a slight deviation from the actual and the ideal vapor cycle. So, here we are considering the efficiency of pump and the turbine with respect to the isentropic efficiency. So, Ws is nothing but work output at a isentropic process, and Wa is nothing but the actual. The 2S stands for the isentropic process and the A stands for the actual process. So, Ws is nothing but H2S minus H1 divided by H2A minus H1. For turbine, similarly Wa divided by Ws. So, H3 minus H4A divided by H3 minus H4A. So, what are all the chances, otherwise what are all the ways that we can increase the efficiency of Rankine cycle? Because a slight increase in this particular process may have a very big impact in the global market, because most of the electricity generating power plants are working with the steam turbines. So, a slight increase in the efficiency of this particular process have a very big impact. So, what are all the ways that we can increase the efficiency of Rankine cycle? So, we have the ways that we can achieve increase in a Rankine cycle by increasing the average temperature at which heat is transferred to the working fluid in the boiler. That means increasing the temperature of the working fluid, and else we can do decrease the temperature at the rejection. These are the ways that we can able to increase the efficiency of Rankine cycle. So, this can be achieved by any one of these three methods. One is by lowering the condenser pressure, and another by superheating the steam to higher temperature, and the last one is increasing the boiler pressure. Each one have its own advantage and disadvantages that we will look in the upcoming slides. Lowering the condenser pressure. So, this is where we basically try to reduce the pressure at the condenser. So, in order to that, as a result this lowers the temperature at the heat rejection. So, let us see this TS diagram where it is clearly shown that decreasing the condenser pressure increases the net work output, that is the area covered by the process 1, 2, 3 and 4. So, 1, 2, 3 and 4 represents the normal Rankine cycle, and the states 1 dash, 2 dash and 4 dash represents the condition for lowering the condenser pressure. So, by decreasing the pressure in the condenser, so that increases the net work output. So, there will be increase in the area. So, this results in the increase in the work output. The condenser can be operated at a lower atmospheric pressure. So, but this is limited due to the cooling medium in which we are working, because we required certain temperature difference, and moreover that should fall within the saturated pressure value. So, lowering the condenser pressure increases the moisture content of the steam. So, decreasing the pressure at the condenser, So, it may have a possibility of increasing, otherwise it will definitely increase the moisture content of the steam at the inlet of the turbine. This is not a desirable effect, because the vapor quality at the inlet of the turbine should be definitely more than 90%, because the moisture content will damage and corrodes the blades of the turbine, which is not a desirable effect. So, next possible way is superheating the steam to high temperature. This is where we are basically increasing the temperature at the inlet of the turbine. So, let us consider this 1, 2, 3 and 4 gives the state of a normal Rankine cycle, that means ideal Rankine cycle, and 3 dash and 4 dash represents the superheating of the steam to high temperature. So, what happens? So, when we increase the temperature, so at the inlet of the turbine, it increases both the net work output and the heat input to the cycle. And also it decreases the moisture content of the steam at the turbine exit. So, this is the effect. The superheating the steam to high temperature have certain limitations. The limitation is basically because of the metallurgical consideration, the material with which the turbine is constructed is made. So, because the turbine which we are using right now is have a limitation of the maximum temperature at which we can operate the turbine, because of the material constraint is 620 degrees Celsius. So, this is the maximum temperature that we can operate in a turbine which we are having right now. If you want to increase this temperature, then we have to work on new material which can withstand and give the same efficiency of the turbine which we are running right now. Okay. Increasing the boiler pressure. So, basically this increases the temperature at the inlet of the turbine. So, here in this particular TS diagram, we can observe a red zone, which is nothing but a decrease in the work output. So, 2 dash and 3 dash represents the increasing boiler pressure condition, and 1, 2, 3, 4 represents the ideal Rankine cycle. So, there will be a slight increase in the 2 to 2 dash, that means there is a slight increase in the work output with respect to the change from 2 to 2 dash, but it is not that much, because when compared to the increase in the area of in the region of between the saturated dome, the increase in the 2 to 2 dash is very minimal. So, it is not having that much effect, but there is a reduction in the net work output when the state from 3 to 3 dash. So, this have disadvantage, and operating the boiler at a higher pressure will give us opportunity to add more heat to the steam. To summarize this, the increasing opportunity in Rankine cycle can be summarized with this. So, the most of the process which we will try to increase the average temperature at the inlet, else we will try to decrease the temperature at a heat rejection. So, this can be achieved by three methods. One is by lowering the condenser pressure, but in condenser pressure lowering the condenser pressure, we have certain limitation. The limitation is basically depends on the cooling medium. In next is superheating the steam to high temperature. This have advantage. So, like it increases both the net work output and heat input to the cycle, and also it decreases the moisture content of the steam at the turbine exit. But there is a limitation in the metallurgical consideration, because the highest temperature that we can operate the turbine is limited to 620 degrees Celsius, and the final method is increasing the boiler pressure. So, this raises the average temperature at which heat is transferred to the steam. So, that is the advantage, but the moisture content of steam at the turbine exit increases. This is the disadvantage in the increasing the boiler pressure. So, this particular lecture gives you the overall idea of about how the steam power plant and the components which we are using and how in what kind of a principle it is working, and we also saw some of the methods to analyze the particular efficiency of the devices, and moreover we have seen certain methods to increase the efficiency of the Rankine cycle. Thank you.